Hey everybody, Eric Rounds from the Forest Service. I'm a contractor at GTech, and I'm going to be leading up this presentation on a project we've done over the last 3 or 4 years, focusing on canopy cover mapping in Puerto Rico and the U.S. Virgin Islands. Once I go through that, I'm going to hand it off to Nathan to go through a little demo of some of the products that we've created for this project. I have a brief agenda here. I'll try to get through this all pretty quickly so we have plenty of time for discussion and questions at the end. But I'll start with a quick overview of GTech, some background from this project, sort of where it came from, what the considerations were, what the needs were, and what our objectives were. And then I'll jump into some of the meat of the work that we've been doing, the study area, the data sets we've been working with, primarily LiDAR data, walk through some of the methods, which are frankly relatively simple, and then really highlight the products and results. And we have several deliverables that we'll talk about and share links to. We have Spanish versions of things as well as English versions, so we'll highlight all of that. Okay, GTAC, if you're not familiar with it, stands for the Geospatial Technology and Applications Center. It is a detached Washington office, and we provide broad geospatial support for the Forest Service at large. We don't work for a single forest, although we're located in Salt Lake City primarily. We support forests across the country, do a really wide variety of work. We develop workflows, innovation, all geospatial related. We have a fire mapping program, a hazards mapping program, do lots of web mapping and geospatial application development, some of which you'll see here today. We have a training group that provides regular, freely available trainings on GIS, remote sensing, change detection, all sorts of stuff. And through Maya, we were able to partner on this project because there was a clear need for some urban canopy cover mapping, initially in Puerto Rico, but eventually we expanded it to the U.S. Virgin Islands. So just a bit of background on that. Urban canopy cover is really a very important part of our forests. A lot of the time we're thinking about these vast spans of forests in the lower 48, but oftentimes these urban canopy cover areas are overlooked in the grand scheme of things, even though they provide all these extremely important ecosystem services, ranging from air quality, carbon storage and sequestration, energy use, the shade provided by urban trees, especially in the summer, is very important to avoid some of these heat island effects. They help mitigate large water events, stormwater runoff. They're obviously extremely important for recreation and urban aesthetics, things that really can't be overlooked when we're considering livelihoods and just environments in urban areas. One of the problems with this urban canopy cover realm is that we don't have a ton of data. We don't have, across the US and elsewhere, good data depicting the location and extent of urban tree canopy cover. So that was a clear knowledge gap and information gap that we saw leading into this project. Something that sort of compounds that issue is that we need to update those maps relatively frequently, especially in areas like in the Caribbean, where we have quite a lot of hurricane activity. Right around when this project was coming about, it was in the years immediately following Hurricane Maria and Irma, which really caused serious disturbances and ravaged parts of Puerto Rico and U.S. Virgin Islands, as well as other Caribbean islands. And the frequency of these events, there have been hurricanes since, mean that there's a real great need for a replicable workflow for mapping urban canopy cover. So what kind of data is available currently? I'll show you in the next couple of slides a few of the data sets that were readily available at the time of this project, but for one reason or another don't exactly meet the needs of what we're looking for. The first data set I'll talk about is the NLCD, or the National Land Cover Database. This includes a layer that gives you a percent canopy cover raster, just depicting 0 to 100% canopy cover at a 30-meter scale. So each Each of those pixels is covering about 900 square meters. And while that might be quite useful for some broad scale analyses across whole states or territories, when we're looking at the urban environment, it really isn't sufficient for our needs. We want to be able to see individual trees on roads, gaps between the trees, and not just have this sort of summarized percent canopy cover information that we get from the NLCD. Also, it's updated relatively infrequently, although the most recent update for, I believe, Puerto Rico is 2021. Another data set that starts to get closer to what we're looking at is the Coastal Change Analysis Program, or CCAP. This is a program managed by NOAA in which they are producing 2-meter spatial resolution land cover data. You can see a map right here just showing all the different categories, one of which is forest cover. And that is just a simple binary presence or absence of data, but it is far higher resolution and far more detailed than that 30-meter data we were looking at before. Again, another caveat here is that this was produced quite a while ago. The last one from Puerto Rico, I think these are in works and may have been updated since, but Puerto Rico in 2010 and the U.S. Virgin Islands in 2012. And that's just not, recent enough for us to be making land management decisions off of that data. The next one that we saw, this is something that really inspired this project and was something that Maya showed to us and said, is this something that we could do in Puerto Rico and the U.S. Virgin Islands, was this California canopy cover map that was produced through a joint project of Forest Service and Earth Define LLC. They derived this data from 1-meter LiDAR data. And like that previous data set we just showed, it's just a simple presence and absence. We're seeing in green on the left where vegetation trees have been identified. And then they take it a step further and take that sort of just simple presence information and start summarizing it to decision-making admin boundaries. In this case, they're summarizing those percent canopy covers to census tracts and making them available through a web map that users can easily interact with and compare and contrast percent canopy cover in different parts of cities in Southern California. And we saw this as a really, really useful tool and one that we could potentially pilot somewhere else. So around 2020, we started to work with Maya and Nathan and really outlining and piloting an initial workflow. So how do we go from this LiDAR data that is publicly available and sort of disseminated from the USGS, how do we go from this LiDAR data to a data set depicting canopy cover in urban areas? Once we had sort of piloted that out and made sure it was doable and scalable, we really scaled it up. And not only did we focus on urban canopy cover, we just decided to create these products for the entire extent of 2 LiDAR acquisitions. I'll show you a map here in a bit to show you the coverage of them in 2016 and 2018. And then we aim to then summarize those canopy cover statistics to admin boundaries. And then, of course, we wanted to make this data publicly available, easy to interpret, easy to understand how we created it. So we packaged this up, made the data available, made web maps to make them very easily interactable or interactive. And then we also provide some detailed background on how one could replicate this workflow. But before we jump into that, I want to give a brief background on what LiDAR is. I know it's probably a word that if you're familiar with remote sensing or GIS at all, you may have heard, a bit of a buzzword, but it stands for light detection and ranging. It's an acronym very similar to something like radar, which is radio detection and ranging, or sonar, which is using sound. It's essentially a technology that measures distances through the emission of light from a sensor. These can be put on tripods or planes. Usually when we're talking about LiDAR data, we're talking about something collected from a plane. And it's an active sensor that just emits light, and it is measuring the distances and the time it takes for that light to return back to its original source. And from that, we get all sorts of measurements on the tops of trees, the middle of trees, and then ultimately the ground. So this data gives us really incredible 3-dimensional data that we could use to summarize information about the bare earth ground, just the elevation of the ground, canopy height, height of buildings, things like that. Ultimately, once it's collected, we have this really fancy three-dimensional point cloud, they call it, with elevation of everything in the urban landscape and the more rural and forested landscapes. And just to show you sort of what it looks like compared to our normal high resolution imagery, which for in a lot of cases is really fantastic and all you need. But here we have a really high res image of a forest. We could tell some things based on, just the texture of the trees, the color of them, but you can't tell the heights of them from this imagery. And by contrast, this is what a canopy height raster looks like in the LiDAR world, where the red values are tall, the cooler blue values are closer to zero and lower to the ground. We can actually get really accurate measurements of trees. And not only can we measure the tops of them, but you can start to see the gaps in between them, start to see individual trees much better in this way. So we wanted to use the available LiDAR data that was recently collected in Puerto Rico and the U.S. Virgin Islands to map canopy cover at a 1 meter resolution. Here's just a map of the extent of the different acquisitions. Of course, Puerto Rico is quite cloud covered for parts of the year. And because of that, there are parts on the southeastern, eastern extents of the island that are going to be data voids for the two different acquisitions. LiDAR simply just can't see through clouds, so ultimately data can't be collected if there's too much cloud cover. But they're relatively insignificant portions of this whole AOI. You could see that the dark green is the 2018 data voids. The outline is also the extent of these acquisitions. So if you look at that, the 2016 data was collected just in Puerto Rico and some of the surrounding islands, whereas the 2018 data covers both Puerto Rico and the U.S. Virgin Islands. So that's something to be aware of. Our 2016 data products are going to be Puerto Rico only, but 2018 will have U.S. VI coverage. So first step of the methods. How do we even get to that 1 meter canopy height data I was showing you before? It's a pretty simple process. We take a digital elevation model, which just depicts the elevation of the ground, and we subtract it from a digital surface model, or a DSM. These DSMs are simply representing the highest surface across the whole area. So if there's trees, the DSM represents the tops of trees. If there's no vegetation at all, it represents the ground. And just by subtracting that ground elevation, we then take and normalize our values to above ground heights, which leaves us with our canopy height model. A pretty simple workflow that we have plenty of documentation on. The next component of our workflow is building mapping. Now, of course, in these urban environments, if we look at canopy height, we're going to be seeing a lot of these buildings in there. So what we want to do is remove them, because it's going to be one of the most common sources of error in our data sets. And thankfully, there's been some recently developed tools in Esri Arc Pro that enable us to classify buildings in LAS data, LAS data. That is the point cloud data that represents LiDAR. And it's a really simple tool. You give it the point cloud and just click run, and it classifies all of the sort of flat planar surfaces above a certain height, and does an extremely good job at mapping buildings. We just take that classification and we create a polygon that you can see there on the right, depicting building extents. Once we have those buildings and then we have the canopy height data, we'll then just go into the canopy height data. We'll get rid of everything below 2 meters because we are assuming that that is not tree cover. It might be some lower lying vegetation, some fences, some other infrastructure that we're not interested in including in our data. And we also just totally remove the buildings. We just mask them out. So delete them from it. And we're left with something like you see here on the bottom, a simple binary data set telling us green is canopy, everything else is non-canopy, from which we could summarize to greater scales. So again, similar stuff, 2016, 2018, the same area, some differences in canopy cover. Remember, this is post Maria and Irma, the 2018 data. So it would be rather expected to see some decreases in can't be covered due to intense winds and blowdown events. But knowing that this data itself is very cool, but potentially not the most useful for broader scale decision making, we wanted to summarize the data to a variety of admin boundaries and also provide information on the canopy cover percentage in municipalities in general, and then within the urban areas of all those municipalities or territories. So we generated these statistics. They're available in our web maps and in our report. You can see here we did for all 2016 and 2018 Puerto Rico. You can see all the different columns that we have in here. We did the same thing for the U.S. Virgin Islands in 2018, using just different admin boundaries than we did for Puerto Rico. But otherwise, it's the same information. And it really makes this information really easy to compare and contrast from one territory or island to another. So with that, we'll talk a little bit about the accuracy assessment that we did here. Of course, this is a data set we want to make publicly available and give people confidence in. So we did a pretty standard accuracy assessment where we distributed thousands of points across our study area in areas that we deem to be forest, as well as in areas that we deem to be non-forest. And then we used very high resolution imagery from around the 2016 acquisition, as well as from the 2018 acquisition, post-acquisition, and had a skilled interpreter go through and classify canopy or non-canopy. So simple interpretation, and then we take all of that information, we summarize it, and produce some of these stats that you see here. And as you can tell, our accuracies were very high, and we weren't terribly surprised by that. This LiDAR data is incredibly specific and detailed, and because it's measuring the heights of objects on the Earth's surface, it's pretty darn accurate. There's no modeling going on, no sort of interpolation for the most part. So it's really useful data in that sense. But there are known issues and things that can be fixed, but weren't really within the scope of the work that we were doing here. So just wanted to highlight some of these and explain how one would actually deal with these or mitigate the issues. One of the things that we, of course, saw was the inclusion of infrastructure like power lines and other sort of fences or electrical systems in our data set. So here we have some urban areas in Puerto Rico, just showing some of the data that we could see is clearly an error. And, even though they are visually apparent in our data, they really aren't making up a significant portion of our overall data set. So that's why, even though you could see these lines representing power lines and whatnot, we're still getting into the high 90s of accuracy of our data. These can be removed, and we've talked with other experts who advise us on this, and they're all basically in line with this is manual work at this point. There's only so much that you could do in a semi-automated fashion, and then at that point, if you want this data to be as close to perfect as possible, you need to sort of go in and manually edit things. This is another area. We had some of those voids that I mentioned before, and essentially, we created the building polygons from 2018 data only. We didn't then recreate those for 2016. It's a very intensive process, and we were running into some errors with the 2016 data. And because we just masked out buildings using 2018 data, there are some errors in our 2016 outputs that you see here, where essentially buildings just are still in our 2016 data. This is a pretty small area in the grand scheme of things, but it is something we want to acknowledge and make people aware of. All right, the deliverables. So we recently got a lot of this approved to be shown and shared publicly. We have a general technical report, or GTR. It's a really beautiful document. I think our colleague Linda Smith did a wonderful job of putting it together and making it look as attractive as possible, while also sort of making it easy to read and interpret. We took all the data products that we created for this project and made them available. Because we created some intermediary products that I don't think are broadly available, we wanted to share those as well. And those include the canopy height rasters, which are just a sort of intermediate product that we created to get to the canopy cover. Those are very large data sets, so beware downloading them. They're 1 meter mosaic wall to wall, so they're 40, 50 gigabytes, something like that. Also provided the building footprints in our Canopy cover presence rasters. So all of those are easily accessible through this public box app. And we also have two versions of our story map. A story map is an Esri-based web tool that is a sort of a mixture of a web map and narrative. So we're giving you lots of information about how we derive these products, how to interpret them, and sort of combining that with a spatial element so that people can go in and look at the canopy cover percentages in their given area of study. So with that, I'm going to hand it over to Nathan to give a little bit of a demo of the story map and web maps that we've produced here.